Hi, welcome. So the last topic for this week is diffusion models. And I know we've already done a lot. We've done generative adversarial networks, we've done variational autoencoders, but now we will not be doing full justice to Gen AI if we don't talk about diffusion models. So here we go. What is the problem? Why did people invent these diffusion models? Well, we know GAN. If you remember, there is the generator. It converts latent vector z into your output x dash. Your discriminator distinguishes between your x dash and x, and this generator and discriminator together create our so-called generative adversarial networks. The problem is that it creates sharp images, but it's mathematically unstable and prone to mode collapse, meaning it may not just learn anything. Let's say the police become so powerful that the counterfeit, the rogue agency cannot exist, so that's a mode collapse. So this is sensitive to training, and this is why we kind of need all those fancy activation functions, but even then it's not very easy to train, and also the variety is not as much as let's say diffusion models. Secondly, VAEs. So VAEs, if you remember, we have a simple encoder, we have a decoder, and we enforce a KL divergence here between the Z and say the normal distribution, right? So we have a KL between the Z and the normal distribution when doing a VAE. What is the VAE problem? Well, it's stable, it's easy to train, but it tend to be blurry images, and also the variety is low, the diversity. And diffusion model is the best of both worlds. What it does is, it trades sampling speed, meaning it's slow. It's really slow. So it trades sampling speed for training stably and mode coverage. So diversity, variability, yeah, and incredibly sharp images. And this is why we are learning diffusion models. So in diffusion models, what happens is, we start with something which is like a complete noise, and then we achieve our final image, or vice versa. So x₀ is usually the final image. You start with noise, you go all the way to image, and this is the reverse process, and this is the forward process, and more on this in the next slides. So diffusion essentially looks like this, right? So this is diffusion in action. Here we see dye getting diffused in, let's say, water, and once this dye is fully diffused, that is the stable equilibrium of that system. And we kind of model this noising and denoising process of diffusion, and this is why I showed you those diffusion videos. So diffusion models essentially are destroying and then creating information. What I mean to say is, we have our image that we want to generate, and we kind of do this forward pass, this destruction pass, where we start with this clean image x₀, this one, and we iteratively add Gaussian noise over t steps until we reach this pure static. So you see, this is the iteration number 1000, this iteration number 0, 100, 200, 300, all the way to 1000. So what we are doing is very simple. We take an image and we iteratively add Gaussian noise. We add some Gaussian noise, we add more noise, more noise, more noise, more noise. We keep doing that until we reach pure static. This is the forward process. This is easy to do. Making things bad, is usually easier than making things good. So the forward process is very straightforward, and again more on that later. And this reverse process, this creation, this is what we are interested in, right? Because what we want to do is we want to start with that pure static, with that x of t. And for example, in a VAE we start with noise, in a GAN we start with noise, in a diffusion model also we want to then start with this and use a neural network to iteratively predict and remove noise until we recover this clean image x₀. So you see where we are going with this? We say, okay, we want to learn how to kind of denoise the image. So we get a neural network to learn how to remove the noise. Of course, we'll go through details, we'll even cover code, but that is the intuition. the forward process is essentially making things more and more blurry, making things more and more noisy by adding that Gaussian noise, and then we try to learn the reverse process. So, but even the forward process is not that straightforward, and I mean it is straightforward, but there's just that variance trick that we need to remember. So what we might think that, you know, your naive mixing, let's say I want to create this image, all I need to do is, you know, this image is equal to, let's say, my original image. So let's say lambda times my original image x0, and then let's say 1 minus lambda times some noise, and here we are calling the noise, let's say, this epsilon, right? So in general this is okay, but if we add noise without scaling, right, if we say alpha and beta are both a and b are both equal to 1 here, then the pixel values will grow because you have an image and then you add some noise to it, so the pixel values will increase, and if you keep doing that 1000 times, then probably it will become a fully saturated image. Your contrast will go on the other side, right? It will be a completely white image. So the goal is so the image clips blowing up the harsh white and black pixels, and the goal is variance preservation. We must keep the overall variance, the pixel contrast, exactly the same at every step, so the image data remains stable for the neural network. I think this will show you better. So here we are kind of doing that variance stabilization, but here where, as you see, we're just kind of, you know, so t, we're going from 0 to 100, and as we go it becomes peak here and peak here, right? So here we are using this so-called square roots, and I'll show you what I mean by that. But here we are just using, you know, we have values for alpha t and 1 minus alpha t. So we have values for alpha t and 1 minus alpha t, but here the values are different because now we have taken this square root, and I'll show you the math. But remember, this is the same thing, I mean at least math wise, that we were doing when we were doing the weight initialization, because even there we wanted our variance to be stable, and that is why we were dividing by the under root of fan in, if you remember, right? So it's all very related and very simple. The underlying, you know, math essentially is the math of mixing two random variables, and in this case, what are the two random variables? We have x, which is essentially the pixel intensity, and we have epsilon as an independent random variable, which is the injected noise. And let's assume our normalized image and our pure noise both start with a variance of 1. So the variance of x is 1 and the variance of epsilon is also 1. And this is possible because by design this is how we have created it. We have taken the image, we have, you know, subtracted the mean, we have divided by the standard deviation, so our variance is 1. So we have divided by the variance and the variance is 1. And similarly we have done similarly to the noise, because what we are doing is the noise we are sampling from a unit Gaussian. So by definition our variance here is 1, and so we have a unit variance noise. And the law of variance essentially says that when adding independent random variables scaled by a and b, their variances must be multiplied by the square of those scales. Meaning, if we have two random variables x and epsilon, and we have two scalars a and b, then the variance of ax plus b epsilon is a square variance of x plus b square variance of epsilon. Variance of x is 1 because that is what we started with, and variance of epsilon is also 1 because that is what we started with. So variance of ax plus b epsilon will essentially be a square plus b square. And this is what our target variance is, because what we are saying is our a square plus b square should finally be equal to 1, because we don't want the variance to change, right? So this is what we need to do, and all we are saying is that our two epsilons, they have to sum to 1. So what we are saying is our alpha and our beta have to, so our alpha plus beta should be equal to 1. We can also write alpha as beta minus 1 or beta as alpha minus 1. right? So this is just, we're taking alpha to the side, so it becomes 1 minus alpha, right? So what we're saying is, okay, so this is essentially the diffusion step, and so except for the coefficients, everything is really straightforward, right? So what we're saying is, we take the so this is the forward process, right? So we are making, let's say, so we start with x equal to 0. This is our full good image, everything looks nice, right? And then what we are doing is, we are iteratively making it noisier. We are adding this Gaussian noise, and here there is even more noise, right? So this is, let's say, at time t minus 1, and this is at time t. And what are we saying? The image at time t, so this is xt, and let's say this is xt minus 1, should be your under root alpha times xt minus 1 plus under root beta times the noise. Yes. So now what it is doing is, it is just saying that, we are kind of we already have our xt minus 1. So the variance of xt minus 1 is 1, and the variance of our epsilon is 1, and our alpha plus beta is equal to 1. So if we have all these three different conditions, we can make sure that the variance of this variance of our xt will also be equal to 1, right? And that is all that there is, right? So we just want our variances to be 1. But now we also want to do one more thing. What we want to do is, we know how to get to xt from xt minus 1. This is simple. You do a under root alpha of xt minus 1, and then you do a 1 minus alpha under root of your noise, of your epsilon, of your n of 0 comma I, right? But now I also want to know how to get to xt directly from x naught, right? Because that is what I will usually be doing in my code. I will have my good image, and I would want to, noise it for some t number of steps. So to get to x1 from x0 is simple, because I can just use this equation. But can I go from x0 to, let's say, x100 without doing this in a loop, without doing it iteratively 100 times? And the answer is yes, if you write down the math, and it's very simple. So let's look at the math. So what we are doing is, it's all high school math, by the way. So what we are doing is, we are saying, okay, we have our xt, and our xt is essentially this function, right? So let me also rub this off. Okay, so let me rub this off. And now let's just concentrate on the equation, right? So we have our xt, and xt is a function of xt minus 1 and your Gaussian distribution. And then what we are saying is, we are going to substitute this xt minus 1. What is xt minus 1? Xt is under root alpha xt minus 1 plus under root beta, this Gaussian. So then xt minus 1 would be similar. Xt minus would be under root alpha t minus 2 plus this Gaussian, right? And then we have this alpha outside, and then this term remains as is. And then we do it one more time, right? We, instead of x, so we have now opened it up. So we've just multiplied things together, and these are the three terms. And then we do it one more time. What we are saying is, okay, we want to write this xt minus 2 in terms of xt minus 3. So it then becomes alpha times xt minus 3 plus beta, and then the other terms, right? So this term and this term. Now we open this whole thing up. So xt becomes this term, so it's just this multiplied by this, and then this term, which is this multiplied by this, and then this and this, which are just this and this copy. So our xt is this. So now if you look at it, you will notice, that, so this is what our this is what we got in our previous slide, just to kind of see. So this is what we got in our previous slide. This is something that I want you guys to remember, right? It's very simple, but yes, it's a little bit involved. There is a little bit of algebra. The equation looks nasty, but actually it's very easy, right? So I want you to remember this equation, and I want you to kind of see if you see some pattern in here. But what I'm saying is that now my xt, instead of being a function of this t minus 1, I want it to be a function of my target t directly. And if you look at this, what we are saying is that since alpha is less than 1, because alpha plus beta is equal to 1, as there are more and more steps, this alpha to the power t will kind of approach 0, right? Because it's the smaller than 1 continuously being powered. So it's maybe 0.3 into 0.3 into 0.3, so on. So it then is almost equal to 0. So we kind of ignore this term. But the rest of it, if you think about it, you look at this, the equation, right? So it's essentially, look at the beta term, right? So we take, like, for example, the beta. So we take beta out, and then you have alpha square here, and then you have alpha here, you have alpha square here, and so on. So essentially the total variance becomes beta plus alpha square beta plus all the way to alpha t minus 1 beta. So our alpha t minus 1 beta is alpha square beta, right? So alpha square beta, and all of under root, of course, but I mean here we are just dealing with the total variance. And if you were to then, so this is essentially a Gaussian, this is essentially a GP, right? It's a geometric progression. And the formula to sum up this GP, to sum up this GP is the first term a into 1 minus r to the power n. What is r? R is essentially the factor, and the factor in our case is beta, right? So the factor in our case is beta. And what we are saying is, okay, it's a, which is the starting point, which is in case beta, into 1 minus r to the power n. Sorry, in our case r is alpha. So 1 minus alpha to the power t upon 1 minus r. So 1 minus alpha is again beta, so we have written beta here. And then this beta and this beta gets cancelled, so it becomes 1 minus alpha to the power t. And now if our xt we can replace with this 1 minus alpha t under root, right? Because the first term we start from here, and then we take this term, which is the sum of everything else for the variance of the Gaussian, and this becomes here. And this gives us an equation that we need, which basically says that, okay, if you have your first nice image, the the image that does not have any noise, I know how to create. So this is our x0. I know directly how to create xt, and if t is large, there will be more noise. If t is less, so if t is, let's say, 100, there will be like really a lot of noise, and if t is just 5, there will be less noise, directly by looking at this. And what is this? This is essentially the multiplication, right? So it is essentially this alpha to the power t kind of a term, where you're multiplying all the alphas from previous, from here, and you are then calling it alpha dash t. But the good news is that this is your Gaussian, this is your input image, right? This is your original image, and also this is your alpha, the alpha to the power t. And the good news is that if you just have your input image and your Gaussian noise in one step, you are able to get from your initial image to the noisy image. So remember, we are doing the forward pass. So we are actually making the image worse. We are just putting in noise. Later we'll do the learning, we'll do the neural network, which will remove the noise. But here, till now, we're just learning how to input noise. And why do we need to do this? Because we want to use it in code. Because in code, we don't want to write that for loop. And this is code that will give you, we have this noise scheduler. And what is this noise scheduler doing? Well, noise scheduler is first, doing basic setup things. We set alpha to be 1 minus beta. It's a linear schedule, which just says that beta increases linearly from beta start to beta end. We also have, our alpha bar, which is the cumulative product of all alphas, all the way from, alpha to the power 1, 2, and so on. And then for numerical stability, we do some simple things. And then this is where we add noise. And this is where we use this reparameterization trick. And look what we're doing here. So we are saying square root alpha bar t is essentially your square root alpha bar t, and we are doing many of them together, right? So we are using this v of minus 1 1, and then we are saying square root of 1 minus alpha bar t is nothing but this square root of 1 minus alpha bar t of t, and then we are again doing this view, and then the magic formula xt, this is what we were after, is square root of alpha bar t into x0 plus square root of 1 minus alpha bar t into noise, and then we return both xt and noise. And that's it. That's all that there is in our forward prop, or that's all that there is in our forward pass of the diffusion model in making the image noisy, in creating data essentially, right? Because this is the data that we will give our neural network. We'll give it a dirty image. We already have the clean image because we made the clean image dirty, and then we will ask the network to predict this clean image. But there are some nuances, and that's what we're gonna look at now.